how to solve the heat equation and the wave equation, but this time with either with source currents or charges. So what I mean by that is currently we've been looking at these only homogeneous partial differential equations, right? So partial u over partial t equals partial squared u over partial x squared, right? But now we're going to look at how we can solve inhomogeneous partial differential equations when there's a term q. So the way we approach this is by defining two new functions. We say u of x comma t, our function, is equal to r of x comma t plus v of x comma t, right? And okay, in addition to boundary condition, in addition, we're going to look at the boundary conditions, where we've also only been dealing with homogeneous boundary conditions, but now we're going to learn how we can deal with boundary conditions where we have where we have functions with respect to time. So if we have, say, u of 0 comma t equals a of t equals some function a of x comma t and or if u of and ul comma t equals b of x comma t. Okay, so to kind of understand how to do this, we're going to do it in cases, starting with the simplest case where we have still a homogeneous differential equation, partial u over partial t equals partial squared u over partial x squared. But inhomogeneous boundary conditions. So say when u of 0 comma t is equal to 1 and u of l comma t equals 4. What we can do is we can turn these boundary conditions that are currently inhomogeneous into homogeneous boundary conditions by using a reference temperature distribution. So using this equation I wrote out here, we'll define some r of x comma t, which has the same boundary conditions as u of x comma t. So r of 0 comma t equals 1 and u of l comma t equals 4. And then r of x comma t can be as simple of a function as we want. So we'll just define it to be a linear function, and what would be the steady state for this temperature distribution, which is 3 over L times x plus 1. Next, what we're going to do is, so now that we have this, v of x comma t, the boundary conditions for v of x comma t are just 0 and 0. So v of 0 comma t equals 0, and v of l comma t equals 0. And this we know how to solve. It's just the Fourier sine series. So the sum from, so v of x comma t is now equal to the sum from n equals 1 through infinity of a sub n sine of pi over Lx I think I skipped this step, but obviously we can break, we need to include the t term so that it'd be e to the minus lambda t, where lambda is equal to n pi over L whole squared. And then an a sub n is just an a sub n is equal to 1 over L times the integral from 0 through L of, this time instead of, so if the initial conditions for u of x were, say, u of x comma 0 equals f of x, then the initial conditions for, similar to how the boundary conditions for v of x change, the initial conditions would also change. The initial conditions for v of x comma 0 would be f of x minus whatever the initial conditions are for our r of x comma t, which in this case would be 3 over Lx plus 1. So minus 3 over Lx minus 1. And so here, instead of doing f of x, we would say f of x minus 3x minus 1 times sine of n pi over Lx with respect to x. And then we can just sum v of x comma t with r of x comma t to get our u of x comma t. And so this is the simplest case where we have a homogeneous partial differential equation and inhomogeneous boundary conditions. And you can make these boundary conditions more complex, adding, taking for example u prime. Just as long as r has the same boundary conditions as u, this method will work. That is, until you start changing, until the boundary conditions start changing with respect to time. So that'll be the next example that we look at. So here we'll take pretty much the same exact equation, and we'll say it's an inhomogeneous boundary condition where, but still a homogeneous source, still a homogeneous partial differential equation, so no source. And we will try to solve this now. So this time, when we do u of x t, u of x comma t equals r of x comma t plus v of x comma t. Well, r of x comma t would be equal to a of x comma t plus b minus a over L times x, right? And this is the simplest equation we can write to fulfill our boundary conditions. But you'll note that now r changes with time, which means that our partial differential equation, when we rewrite it with respect to v, will change, because if we write partial u of t is equal to partial r plus partial v over partial t, this is an r, and that equals partial squared r plus v over partial x squared. Well, we'll need to, this time, r doesn't, the derivative of r with respect to t and with respect to x whole squared doesn't just equal 0 like it did previously. This time, it will be non-zero. And so we have to include that in our calculations. So we'll say that partial v over partial t equals partial squared v over partial x squared. But this time, plus partial squared r over partial x squared minus partial r over partial t, which you can solve for by taking the derivative of this with respect to time, with respect to x. With respect to time, it would just be a prime of x. Well, it'd be, you could solve it, but abstractly, this is what our new equation will look like. And we'll call this term right here, we'll call it q bar. And you'll notice now that we are now dealing with an inhomogeneous partial differential equation. And the question becomes, how do we solve it? Plus q bar. Well, what we'll do is we will treat it as a homogeneous equation first, and solve it as a homogeneous equation first, and then reintroduce the source charge when we're dealing with the constant, which the coefficient. So v here equals v here, we'll say for now that we're solving partial v over partial t. And we'll say it's equal to partial squared v over partial x squared. And so we'll do what we usually do with these kind of problems, where we do separation of variables. V is equal to some phi of x times h of t, and we've done this before, but v would just be equal, the solution to v of x comma t would be equal to the sum from n equals 1 to infinity of a sub n. This time, our coefficient would be a function of time times, looking at our boundary conditions, we know that because our reference temperature distribution had the same boundary conditions as our actual temperature distribution that we're solving for, that V's boundary conditions would be 0. So V of 0 comma t equals 0, and V of L comma t equals 0. And so this would be a Fourier sine series. You can write sine of n pi over L x times e to the minus lambda t, where lambda is equal to n pi over L squared. Now, what we need to do now is we just need to solve for our coefficient. And what we can realize is that, and I'll save the math, but because our coefficient varies with time, we, instead of doing using the normal equation we do to solve for our coefficient, we now have to do this eigenfunction expansion, kind of where we take the derivative of a, sum it with lambda times a sub n, and this is now equal to the integral from 0 through L of our q bar times sine of n pi over L times x dx. And note that we dropped the we're now solving for our coefficient, which we have to then take from 0 through L of sine squared n pi over L x dx. Great. So now we just need to solve this new differential equation. And the way we do that, and we'll label this huge term that we've written out over here as q lowercase q sub n of x comma t. Right? So the way to solve this is we have to turn these two terms, we have to bring them into one term. And what you'll realize is that if you multiply both sides by e lambda t, and this is a standard thing we do with our ordinary differential equations, if you multiply both sides with e lambda t, you get the derivative with respect to time of a sub n e to the lambda t is equal to q sub n e lambda t d lambda t. And then you can take the integral so that you get a sub n of t is e to the lambda t minus a sub n of 0 is equal to whatever the integral from 0 to t of q sub n e to the lambda t dt is. And then simply rearranging the terms gives us the formula for a sub n of t equals a sub n of 0 plus the integral from 0 through t q sub n e to the lambda t dt divided by or multiplied by e to the minus lambda t. And to find a sub n of 0, we use a similar method that we would do for normal constant coefficients, where we realize, well, when t is 0, we can just use our normal formula of 2 over L times the integral from 0 through L of f of x minus the initial conditions for our r of x, which would be the initial conditions for r of x would be r of x comma 0, so minus our r of x comma 0, which you can solve for by plugging t into your reference temperature distribution, and then times sine of n pi over L, all with respect to x. And so you might be wondering, like, what this all means, but basically we now have our formula for v of x comma t, which if we sum with our r of x comma t formula gives us u of x comma t, and the coefficient of v of x comma t comes from this equation right here, where q sub n is just this integral that you can solve for, and a sub n of 0 is this integral that you can solve for. And so it's a lot. it becomes a lot more complicated when you have an inhomogeneous solution. But you can see here how when we have inhomogeneous boundary conditions, and also now when we have inhomogeneous partial differential equations, you know how to solve it using these formulas. So I hope that made sense. Next video, we're going to look at higher dimensional partial differential equations and the Bessel function.